Right. So here are some additional examples. Oh, that's not what I want to do. Of forces. So a big idea that we're going to use with a lot of the calculations is Newton's second law, which is this. Acceleration is directly proportional to the net force, inversely proportional to the mass that's being accelerated. So first question here, example 0, is a student is sitting on a smooth rolling chair. That implies no friction. Combined mass of the student in the chair of 80 kilograms. The student then grabs a 10 kilogram fire extinguisher and turns it on, propels herself with an acceleration of 0.25 meters per second squared. What's the force provided by the exhaust for the fire extinguisher? So if we look at this, the total mass is 90 kilograms because the extinguisher is at least initially 10 kilograms and the chair in person is 70. And so to get the girl and the chair and the extinguisher to accelerate at that rate, you need 22.5 newtons of force. So in real life, the question is, would you expect the acceleration to be a little more or less than this? The thrust was really 22.5 newtons. So I would expect it to be a little bit more as time goes on, because the mass is, if the thrust is constant of 22.5 newtons, I would actually expect that the mass of the situation is decreasing as the exhaust leaves the fire extinguisher. So I'd expect the acceleration to increase slightly. Same force, less mass as time goes on. And then down here it talks about in real life we'd expect the actual thrust would be a bit less or a bit greater. That one, if there is friction on the chair, then the thrust would probably have to be a bit more than 22.5 to cause that rate of acceleration. And the reason is because there would be some friction, probably, maybe a minimal amount, and therefore friction would have to overcome that. Sample 1 here. Batman of mass 80 kilograms accelerates upwards at 3 meters per second squared due to the thrust on his jetpack. Ignoring air resistance, A, draw a free body diagram, B, determine the amount of thrust. So the thrust has to be greater than the gravitational force, which is mass times acceleration due to gravity, symbolized by the lowercase g. So we would have a larger arrow up, a smaller arrow down. So if we start with Newton's second law to determine the amount of thrust, we have F net equals m times A. Thrust minus the gravitational force is equal to mass times acceleration. So T minus mg equals m times A. mg is 80 kilograms times 9.8 newtons per kilogram. The acceleration was 3 meters per second squared, so we get a thrust of 1,024 newtons. So hopefully that makes sense. So the upward thrust should be greater than the pull of gravity. Sample 2, poor drawing here, but we've got Tarzan on 2 vines. Each is being pulled 60 degrees from the horizontal. It says find the tension in each vine. Well, in this case, since they're at the same angle, proportionally, the vertical component of each of these vines' tensions will add up to the downward component of Tarzan's weight. So the weight is equal to both tensions' vertical components. So first of all, I found Tarzan's weight, mg, 980 newtons. We've got 100 kilograms of mass. Next, figuring out that the vertical components, again, in each have to pull upward against that. I'm writing an algebraic equation for this. So T1 vertical plus T2 vertical equals the weight. T1 sine 60 plus T2 sine 60 equals 980 newtons. But if they're the same angle, T1 would equal T2, so we would call those T. So 2T sine 60 is equal to 980 newtons. The tension in each one would be 566. So if it wasn't true that they were at the same angle, the tensions would not be the same. And the horizontal components, in other words, the left component of the first tension and the right component of the second tension would have to be equal. And then you could solve for T1 in terms of T2 or T2 in terms of T1, and then progress forward that way with only one unknown tension variable. Force sample 3. So assume a student is dragging a bag of leaves based on the free body diagram shown. There's friction, there's an applied force, gravitational force. a normal force. Determine A, the net force. Well, there's no vertical net force, so horizontally it's 38 newtons to the right. And then B, the acceleration. So A equals F net over M tote. Well, the net force is 38 newtons. To find the mass, I have to take the weight of this, divide by 9.8 to get the mass. Why? Because weight equals M times G. So M is equal to weight divided by G. So that's 6.17 kilograms. So that gives me a 6.16 meters per second squared to the right. The coefficient of friction is the force of friction over the normal force. A normal force is the interaction up from the ground. On a level surface and with no other things going on, it would oftentimes equal the gravitational force. So that is 60.5 newtons. So 22 over 60.5 gives us a coefficient of friction of 0.36. There are no units with this because newtons is on top, newtons is on bottom, and that cancels out. Sample 4, Spencer and Marissa are part of the stage crew for theater. They must quickly move a 158 kilogram baby grand piano off stage by applying a force of 550 newtons to the piano. If the piano attracts or accelerates at 1.1 meters per second squared, find the force of friction, be the coefficient of friction. So now we're working backwards. We've got an acceleration and an applied force and a mass. So essentially we're having to find this frictional force. So first of all, drawing the free body diagram. And again, assuming G is 9.8 meters per second squared or 9.8 newtons per kilogram. The vertical forces are balanced, so the horizontal forces cause an acceleration. So thinking about that, we've got an acceleration of the net force over the mass. That's an applied force minus the force of friction divided by the mass. And so we've got F applied minus F friction is equal to the mass, which we know, and the acceleration. So essentially this tells me 550 minus friction is equal to 173.8. Friction is 376.2 newtons. Figure out the coefficient of friction, force of friction divided by normal force. And the normal force is mg on a level surface, 1550 newtons. So we get this from part A divided by the normal force. That's 0.24. Sample 5 is the final sample. So we've got a 200 Newton box here hanging from 2 ropes. One rope we're going to assume that is very ideal, is exactly horizontal. The other is at an angle 60 degrees from the horizontal. So this is 200 Newton mass, or 200 Newton weight is hanging from string C. I want to focus on this point right here to determine the tension in each string. Well, big idea, the net force at this point is going to be 0. So as it is for any point that's in equilibrium. So first, I want to recognize that the tension C upward would also equal 200 newtons, seeing as how the weight downward is 200 newtons. Next, I want to recognize that the leftward tension of this, which is the entire tension, would equal the rightward component of this. And the vertical component of B would equal 200 newtons, because it's the only thing that's pulling up at this point. So I'm going to say that tension of B sine of 60 degrees, which is this side right here, is equal to the tension of C, which is 200 newtons. So I can use trig to find that the tension of B is 231 newtons. With this one, it says recognize the force left from string A has got to equal the rightward component of string B. So now we know string B is 231 newtons. The horizontal component of that, which is a cosine of 60 degrees, which is this part, would equal the tension in A. So that's going to be 116 newtons. So there's a lot going on there. I'll put the PDF of this as well, and hopefully both of those will make some sense. And if you look at these, you can practice some of these or go through these as you're doing your homework.